Greetings. I hope this video finds you well. Today, we will be doing something of a thought experiment involving chemistry. Or, more accurately, can chemistry answer this question? If they were real, how would dragons breathe fire? Well, me and a friend of mine have come up with two theoretical answers to this hypothetical question, each of which will be shared with you today.
How can dragons breathe fire? We've all seen the pictures of dragons exhaling fire, so the easiest thing to do for this theory would be to ask, what causes fire? At least in realistic settings, fire needs two things to start: a spark and fuel. The spark brings it into existence, and the fuel keeps it going. With dragons breathing fire, it seems like they need a sparking mechanism either in their throats or mouths, and then a refueling fuel system that can be accessed at will. This isn't so easy to find with research. How does a living being keep a refilling supply of fire fuel in their mouths or throats, especially when said fire fuel is going to have to be a gaseous or an alcoholic liquid? Some of the other theories in this video might cover that, but for me, I started looking for alternatives. That's when I came across chemicals that ignite upon interacting with oxygen. Interesting. So if this dragon could store said chemicals that ignite upon contact with oxygen, then it wouldn't need a sparker or a fuel source. It would just need a stash of said chemicals, and a way to get them into the air without igniting them inside its own body. Well, I can work with that. For my portion of this video, I will be covering aerosol phosphines, as an answer to how dragons can breathe fire. I will explore the idea of what phosphines are, how they would chemically work, and how I think a dragon would be able to store or replenish their supply of these chemicals. But to start, what are phosphines? A phosphine, or pH3, is a colorless gas that smells terrible and is extremely toxic. A concentration of 500 parts per million can kill a human in about a half an hour. Even if the phosphine gas didn't ignite, it would still roast its intended victim, just probably in a more prolonged and painful way. Now you can already spot the obvious problem with this theory, which is how in the world can a living being store a gas inside of its body? Well, we can at least work with that. You've probably noticed how your body stores gas. Every now and then you will burp after eating or swallowing too much air. Gas gets trapped down in your digestive tract, and your body has to release it in order to make sure your digestive system keeps running smoothly. This happens with reptiles too, not just mammals. Thus, it's not that far of a stretch to say that a dragon, or in other words, a giant lizard, could store phosphine as a gas in its body and burp it out, thus releasing it into the air and causing a fire. But doesn't phosphine gas ignite upon interacting with oxygen? So wouldn't burping just blow up the dragon as it's trying to get the phosphine out of its system? Which is a legitimate question. Well, our bodies also store liquid. We store it in our organs and brains and hearts and veins. And we as humans can release liquids through our mouth. We've all retched at some point, or spit out saliva. Heck, we've all probably sneezed at some point. Every time we do that, we are voluntarily emitting a liquid from our bodies. Now, phosphine is a gas that boils well into the negative Fahrenheit, but if it was stored under pressure in the dragon's body, then the minute it left the pressurized system and exited the body as a liquid, it would vaporize back into a gas and thus ignite into a fire. But the question becomes, how could the body store something under that much pressure? Well, that's where aerosols come in. What's an aerosol, you might ask? It's a solution between a liquid and a gas. Think of a dry shampoo or a fog. They are wet, but they are also gases, which is cool, right? Since aerosols require less pressure to store, only 2 to 8 times the atmospheric pressure, it would be a more viable option than a complete phosphine liquid. Let's imagine a situation in which the variables I have described would thus far work. You know how the top of your mouth has that little hole that connects to your nasal system? Let's start there. Say in a dragon, that hole connects to a pouch of sorts. This pouch is lined with a thin layer of strong metal like steel. Inside the steel pouch, an aerosol phosphine is stored under pressure. When the dragon so wishes, the pouch will open up and the aerosol will spray out, flowing past the teeth and into the open air where it will ignite. But this leaves the question, how will the dragon replenish said supply of phosphine? Well, there are plenty of rocks out there known as phosphorites, or rocks with high concentrations of phosphorus. The dragon could eat said rocks, and it would immediately be able to work with phosphorus. All the dragon's body would have to do is extract and transfer the phosphorus to the steel pouch and react it with hydrogen to make the pH 3. If a human body can extract sugars and fats from foods to use around the body, then it's not that much of a stretch to imagine the dragon could have a system inside of it that extracts the phosphorus from the rocks it eats. But if that's too hard to wrap your head around, there's another way. Aluminum phosphide, or ALP, is used as a pesticide in modern society. It is an inorganic solid that reacts with moisture, water, to create phosphine gas and aluminum hydroxide. Since it's inorganic, the dragon would need to consume both aluminum and red phosphorus to create it, but we're left with a similar situation as the last scenario. The dragon consumes phosphorus and aluminum, reacts them to create the ALP, sends the ALP through a passage to the steel pouch, then reacts it with moisture under pressure to contain the phosphine aerosol. The remaining aluminum hydroxide could then be extracted by the dragon's systems out of the pouch to be used in other places or gathered as waste. Okay, so now we have a working system. Now the final question to tackle is, where might this dragon be able to thrive? After all, we just stated it need to consume large amount of phosphorites in order to breathe fire. Phosphorites are often found near the ocean, as oceanic fossils generate phosphorus. Thus, this particular dragon would need to live near an ocean, preferably either near or in some sort of cave next to the ocean. It could chomp on all the phosphorites it'd like there, and perhaps use its fire-breathing ability to host beach parties for the other unnamed fantasy creatures that might exist alongside it. In conclusion, aerosol phosphines are a valid theory for fire-breathing dragons as long as certain conditions are met. The dragon will have to have an internal system that will hold the phosphine gas under pressure, and it will have to consume and react phosphorites to make the phosphine gas. Seeing as humans and reptiles are able to store gases and liquids in their bodies, and are able to extract necessary materials from food, it's not that far of a stretch to believe. And while phosphine gas igniting upon touching oxygen isn't exactly fire, it is something close that is plausible enough for the purposes of this presentation. And with this theory coming to a close, perhaps you might find a better theory coming up if this one isn't your cup of tea. With that being said, on to the next portion of the video.
In a nutshell, this theory proposes that dragons can exhale a certain gaseous chemical compound that combusts when it reacts with air. So, after somewhat extensive research, I have come to the conclusion that a chemically accurate dragon would eat sand and bananas. Allow me to explain. One compound that combusts in air is called silane, which can be formed by reacting the silicon in the sand with magnesium, which can be found in food such as bananas, to form magnesium silicide, and then reacting that with hydrochloric acid, which is also stomach acid. So, our chemically accurate dragon would need to eat both sand and the bananas, and have some organ that could facilitate the formation of magnesium silicide. The magnesium silicide would then be sent to the stomach and react with the hydrochloric acid, forming silane gas. Finally, the newly formed silane gas would then travel to the throat and be exhaled, causing it to react with air and make
Fire! Fire! Fire!